All right, hello everyone. Welcome back to the fourth and final lecture in our mini course series on two seagull spaces.
Great. So since this is the last talk, let me just thank the organizers again one more time for the invitation. It's been a lot of fun to talk about these things, and thanks to all of you who've stuck it out through the whole mini course. So I didn't really know what to call today. I said the conclusion, but then I don't know, in some ways it doesn't feel very conclusive because there's lots more that you can do. So the conclusion, question mark, I guess. So I wanted to just quickly recap from last time. So I'm just gonna cheat and put my notes back up here. So we talked about this example of a two seagull set from a finite graph. So we said, well, we define a simplicial set X sub G, or just X, that has just a single 0, 1 simplex. Single 0 simplex that we denote by the empty set. One simplice is given by the subgraphs, and then we have in general n simplices given by subgraphs equipped with an ordered partition of the vertices, and the number of sets in the partition are given by that n. And then I gave an example. So said, well, if we took this graph here, just with a string of 3 vertices and 2 edges, then I sort of wrote out what all the one simplices would be, what all the subgraphs are, and then sort of gave a, well, representative sample of what kind of things are happening in X2, and, well, still more vaguely what happens in X3, since the number of simplices blows up pretty fast, even for a small graph like this. And then I talked about the face maps, and this is given by, so in the assumption that the blue set in the partition comes before the pink one, our face maps are given by either omitting or merging. So in the case of D0, we just omit the first subset and are just left with whatever's in this pink one. D2 is the other way around. We omit the second one and keep the first one. And then D1 is just given by taking the union. And if we had higher simplices where the outputs of the face maps were still partitioned, it would just be a unioning of things in the partition. And then the degeneracy maps are just given by inserting empty sets in the partition. So S0 would be you make the empty set come first in the partition, and S1 would be where you make the empty set come second, again in our blue before pink ordering. Okay, so that was all we had time for, and so I did not get a chance to explain why this was two seagull. So okay, so the reason, so again, I'm just going to give sort of a representative, here's an example of a two simplex and why it's determined. Sorry, 3 simplex and why it would be determined. So again, I'm going to use the two seagull map associated to the triangulation where we have an edge from 1 to 3. So the two seagull condition here would be saying that if I have, so these are the faces in a 3 simplex given by D0 and D2. So I have D0 and D2. These are both maps to X2. And then the shared 1 simplex between them, this map is D0 and this map is D1. And so in order for the desired map to be weak equivalence, we would need for this to be a pullback or yeah, it'd be a strict pullback in this case since everything's discrete. So here's an example of a 3 simplex. So I'll take the subgraph just with all 3 vertices and just this one edge. And if it's a 3 simplex, then I need to have 3 subsets in the partition. So yeah, I'll say A comes first, B is second, and C is third. So if we apply D0, so that's going to mean just leaving off A, I'm left with the rest of the graph that remains. And now I do a color shift. So pink comes before purple. So pink becomes blue and purple becomes pink. So again, this is how the face maps work, one dimension up. So now D2, if this is a 3 simplex, this is now an inner face map. And so, but it's the second one rather than the first one. So that means we're going to merge the pink and the purple. So in this case, the graph is not going to change. It's just going to be the partition. So we still have this A as the first set in our partition, but now these two are going to merge and we're going to get B and C and the edge between them. Okay, so now we're in a more familiar setting. So D0 is just going to leave off the A and we'll just be left with the edge from B to C. And notice that's what the D1 map does here too. It just merges the B and the C. Okay, so the question is, if all you had was the data down here, would you know that you could reconstruct something up here where this was D2 and this was D0? And if you inspect this, you could say, well, yes, this is going to tell you what the whole graph is. And then this partition here tells you how to break this up. So you would, in fact, be able to reconstruct this. And again, that's just the idea for why, not a proof, but just sort of an illustrative example for why, in fact, this simplicial set is 2 Siegel. Okay. But then, well, we like things that are strictly 2 Siegel and they're not 1 Siegel. So here's an example of why this is not 1 Siegel. And it's not 1 Siegel for a couple of different reasons. So if we look at the 2 simplices, so I'm going to have this similar partition, but different graphs. So I can have the subgraph that's AB, just the vertices, or I can have AB equipped with the edge between them. But in both cases, I'm going to have A come first in the partition and B second. Now, the 1 Siegel maps are given, or at least the 1 Siegel map from a 2 simplex to 2 copies of the 1 simplices. These are just given by the face maps D0 and D2. So when I take D0, I'm just left with B. When I take D2, I'm just left with A. But that is the same thing that I get over here because I sort of lose the data of this edge because the edge isn't contained in a single partition. It gets lost when I take these 2 face maps. So this example shows that if I take this Siegel map, D2, D0 from X2 to X1 cross X1, that this is not injective. Because each of these 2 simplices is going to have image just A comma B.
And then there was also a question in the chat just about whether there's any color on the bottom right portion of the square commutative diagram.
So it just depends on what you want to do. Since 1 simplices are just subgraphs, I kind of just don't draw them. Technically, you could apply the definition and say, well, it's a partition of the vertices into one set. And so I could just circle it in blue, but I usually just omit that because it clutters the notation. So I think in our paper, we actually do give them a single color, but I wasn't doing that here. Was there anything else? Okay. But in fact, this in general, the one Siegel maps are also not surjective. And as an example, we can't compose, say, the subgraph, say AB with the subgraph, say, BC. And the reason we can't do that, right? The way we get our D0 and D2, the images of these two maps, D0, well, at least when I feed in a particular thing, what you get from D0 and what you get from D2, in fact, have to be disjoint because it's coming from things that have been partitioned. So you can only compose things, subgraphs that are disjoint from each other. There would be no way to partition a graph because B would have to be in both sets in the partition, which is not possible. Okay, so part of the, well, let me just ask if there are any further questions. Okay, so part of why I wanted to introduce this example, I mean, besides the fact that it's just a little more interesting, hands-on, but also a little more interesting than the ones that we've talked about before. In particular, the previous examples we had, this map was in fact injective, it just wasn't surjective. But I also wanted to talk about the Hall algebra because there's kind of some interesting features that we can see. It's also, so it's going to be a more interesting algebra than what we got for the partial monoid case, but much more hands-on and describable than the Hall algebra associated to a Lie algebra, which tends to be quite large. So we do, I mean, as I talked about last time, we'll get an algebra whenever we have a reduced two Siegel set. So when x0 is just a point, and otherwise we'd get a more general algebroid or k-linear category. But in this case, it is just a point. So we do get an algebra. This is going to just applying the definition we had before. Sorry, this is the vector space spanned by, well, by definition, this is just the elements spanned by the elements of x1, but here our elements are these subgraphs of G. We can give that a little bit more explicit of a description. And now let's look at the multiplication. So again, just by definition, if I have, well, two of these basis elements, so I'll write them as H and K to suggest that they're subgraphs. By definition, this will be the sum over other subgraphs J, and then we have some coefficient GHKJ. Now, so in general, these all are just supposed to be one simplices, so they're just subgraphs of G. And we know that, again, just by definition, GHK is going to count two simplices that look like this. Okay, but if we think about that, so I mean, these are two simplices where D0 is K, D1 is J, and D2 is H. And if we think about the face maps that we've been using before, well, we're looking at subgraphs J, because J is D1, that's where we recover the subgraph without the partition. So these two simplices will be given by subgraphs J with a partition of the vertices into two subsets such that H and K are full subgraphs on those two sets that are necessarily disjoint from each other. The other thing, and I think I didn't emphasize this last time, this is always the case for a reduced two-Siegel set in its Hall algebra, is that empty subgraph. This is our degenerate one simplex. This is one of the basis elements of the vector space, but it's the unit element. And that's not specific to this example, but I think I didn't emphasize that last time. Okay. So let's look at a couple examples for just very small graphs. So let's take an even smaller graph than what we looked at before. Let's just look at the graph G with just two vertices and an edge between them. Now, so as an algebra, this is 5-dimensional. So it's generators of the 5 subgraphs. So we have the empty subgraph, just the vertex A, the vertex B, and then we can either take the disjoint union of A and B, or we can take the whole graph itself. And now we can ask, what interesting multiplications can we do? Well, if this is the unit element, then we're not going to have any interesting multiplications with that. It's just going to act as a multiplicative identity. And so by the argument above, we can only interestingly multiply things that are disjoint. So the only other things that are disjoint here are A and B. So this is, so if I multiply A and B, well, there are two things that I can get. And it depends on whether I include the edge or not. So this multiplication would be the sum of these two subgraphs. And notice, once I choose the other subgraph, there's a unique two simplex. Once I have the whole boundary here, you can check, once I know the D0, D1, D2, that's going to completely determine the two simplex. So we don't have any extra coefficients here. The coefficients would come if we had two different two simplices with the same boundary. And that just doesn't happen for this flavor of examples. It happened for other Hall algebras, but not for these graphs. So just to see what other kinds of things could happen, another baby example, let me just take a loop on a single vertex A. Okay, so now the subgraphs, there's only 3 of them. So we have the empty one, we have just the vertex A, and then we have the whole subgraph with, so we have the loop as well. And in this case, there is no non-trivial multiplication because we only have the unit element, and then we have these 2 subgraphs, but they're not disjoint because they share a vertex. So there is no two non-empty. Or not disjoint. Okay, so let me write down just some properties of Hall algebras of these 2 Siegel sets from graphs. So things we can generalize by looking at these examples and others. Okay, so one, we've emphasized a bit already that if I have 2 subgraphs that are not disjoint from each other, then when I multiply them in the Hall algebra, I just get 0. So there's no 2 simplex with D0 equal to K and D2. Oh, and I
You
realized
mean that there are not disjoint, so they're
sorry, yeah, they're not disjoint. Yes, thank you. Yes. Sorry, and I realized I neglected to say something up here. You could say, well, what about B with A? This is actually also BA. The 2 simplices that these are arising from are different. They would come from just the reverse partitioning, but in our definition of the Hall algebra, we're just taking the D1 edge. So there is no partition, and so we've lost the information of the partition. So in fact, this is commutative. Come back to write that in a second. Okay, so now if I have, let's look at some cases where things are disjoint. So if A and B are vertices of our graph, then if we multiply those elements, just writing A and B shorthand for the vertex, this multiplication will be a sum over subgraphs H, where the set of vertices of H is just A and B. But then you might have edges. So for example, we saw this above when we multiplied A and B and got, so we had 2 choices there. We had the subgraph with the edge and the subgraph without the edge in the example above. But this principle applies more generally. So more generally, if H and K are disjoint, then when we multiply them together, we just get a sum over J. And now, so the disjoint union of H and K will be a subgraph of J. And the set of vertices of J will be the disjoint union of the vertices of H and the vertices of K. The difference is in that you could have edges in J, and we possibly have many choices, connecting vertices of H with vertices of K that get left behind when we take those two face maps. So to illustrate this, I need to give you a little bit fancier example than what we've seen before. So if we take, say, let's let G be the graph with vertices A, B, and C, and maybe I have only one edge from A to B, but I have two edges between B and C. And let me label them by F and G so I can distinguish them. So now if I took H to be the subgraph AB, and if I took K to be the subgraph that's just C, then if I multiply them together, so my first thing is I can just take the disjoint union of them, but then I can start inserting some or all of the edges. So I could put in just the edge F. I could put in just the edge G, or I could do the whole subgraph. So these are all the possibilities of adding various combinations of these edges connecting H and K. Okay, and then as I went back and explained for that one example, it will always be the case that this is commutative. And that's as seen in that first example. So partitions come in pairs where we just reverse the ordering, and but the partitions are invisible to the Hall algebra structure. Okay, and again, just to write down an observation we've already made, the coefficients G, J, H, K are always either 0 or. So there's 0 if you have things, basically if they're not disjoint, and then you have 1 corresponding to the respective two simplex, which is uniquely determined by its vector. Okay, are there questions?
I have a question.
Yeah.
Do you know if I see, for example, just with the multiplication of two vertices, that this carries the information of what are the edges. But I mean, what general information about the graph can you kind of like get nicely from this whole algebra?
I mean, that's a good question. I mean, I think your observation is correct. And, you know, when you look at how these things multiply and the sums you get, you're sort of, yeah, you should be getting the description for how to recover the graph. But
Wouldn't it be impossible to recover loops? Like there are no loops.
I'm sorry?
You can never recover loops, right? Like a singleton graph with no edges versus like one with a loop, they would give the same Hall algebra, right?
No, they don't, because if you go back up here, like to this example, this has another generator. Because you have the generator from the singleton and you have the generator from the loop. Whereas if you just had A by itself, so it's a bigger underlying vector space if you have a loop, but you just won't be able to, but you could, I mean, you could say, you know, if you had a graph, you know, say you had a graph like this, you know, you could multiply, you know, say you multiply A with the subgraph that's the loop at B, you do get something interesting there. So you would get, you know, either the disjoint union or the thing with the edge between it. And that would be distinct from where, you multiply A with just B. I mean, you'd still get two things, but this is another generator in the algebra or in the vector space. Yeah, so yeah, Angelica, I like that question. I think it's worth exploring, I mean, another question here is sort of there's a couple questions here, which is, which algebras can you obtain, from these particular kinds of two Siegel sets. So you'd have to know sort of, so you know some things here, like it would have to be a commutative algebra. But are there other restrictions on like what kind of algebras you get from these particular flavors of examples? And yeah, and then can you kind of reconstruct? I suspect you could reconstruct the graph in some way, but I don't have a good answer. So
There's also one more question in the chat about under number 4, the partitions that are common pairs and about them being invisible, what the invisible part means.
Oh, yeah. So that's, let me go back. Maybe I'll write it up here. So you can think, if you look at this, I mean, this is coming, let's see, so it's A star B. You have a two simplex. I guess this would be D0 and this would be D1. So that would be the two simplex for A star B. If I did the two simplex for B star A, it's the other way around. So A would come first and B would come second. But, to get from, so this is a two simplex. So to get from here to this subgraph, this is a map D1. This is a map D1. It's just picking up that other face, which is a one simplex, which doesn't have a partition anymore. So sorry, this wouldn't go here, it would go here, but you'd have the same thing.
Okay, so that's an example of like the paired partition.
So this would be a pair, but then like in the definition of Hall algebra, you're just looking at the subgraph that you get via the map D1, not the two simplex with the partitions still encoded. Does that answer your question?
I'm not sure, but it makes it a lot clearer to me. So.
Okay. Whoever wrote it, I'd like to speak up, feel free. All right. So let's see. There's a couple things I'm not going to get to say everything I might like to say, but it's always the case, right? So let me describe a variant of this. And this is recent work with my latest Women in Topology collaborative group. So this is two Siegel sets associated to trees. And these should be rooted trees. So for example, my running example here, I'll use this tree here. And you can do this in a labeled version and unlabeled version. I'm gonna do a labeled version just because you can kind of see what's going on better. So here's an example of a tree. I'm putting roots at the bottom, so A would be the root here. Okay, so this is recent joint work with Olivia Borghi, Pinka Day, Ima Galvez Carrillo, and Teresa Hickstra Mendoza. So in order to define, we want to construct a we want to construct a simplicial set from such a tree and show that it is 2 Siegel. And for this, we need the notion of an admissible cut. And we're going to divide T into a subtree. Well, either containing the root or empty. And well, I'll call this the lower subtree and an upper. This could be a tree, it could be a forest, disjoint union of trees, depending on the cut. So let me give you an example and a non-example of cuts on our sample tree. I'm assuming all my trees are graphs in the sense they've used before. So they always have vertices at the end. If that becomes sloppy, just know that they're there. So something like this would be an admissible cut. So we have a lower tree with this root, and in this case, we have an upper subforest. So whatever edges the cut passes through, they disappear. So we'd be left with this little tree here and then this tree here. We can't do something, we can't do something like this where we wrap around, because you'd have the root, but then with things up here. Roughly speaking, visually, they sort of preserve some kind of level, but this is kind of the easier way to describe it rigorously without resorting to picture. And then you can have multiple sort of compatible cuts on the same tree. So for example, I could say take a cut C1, another cut C2, and then this is an example of where our sort of lower tree is empty, where you just sort of have the cut passing along the bottom. All right, so we can define a simplicial set, which I'll call Y or Y sub T if I want to emphasize the tree. And again, so Y0 is just going to have a single point. Y1 is the collection of all subforests of T obtained from admissible cuts. And so, for example, I could obtain the sort of silly subforest that's just 2 vertices. That would be like if I cut along C1 and I get this left up here. So that, but I claim that if I had the disjoint union of E with AB, neglected my labels here. I could never get the disjoint union. I could never get this forest from a cut because it would require, well, not quite this cut, but it would need something like this, maybe where I go up here and loop around. That's not allowed. So this is a root, and well, the root either needs to be part of a tree, or well, yeah, the root needs to be part of a tree. It doesn't get to become part of a forest. And then I'm sorry, let me do Y2 before I go to YN. So this consists of elements of Y1 together with and equipped with an admissible cut. And if you're paying attention closely, this requires a notion of cuts for forests, which I'm not going to get into. It's a natural generalization of what I've described for trees, sort of a tree-wise cut, basically. And then YN more generally consists of elements of y1 with n minus 1 admissible cuts. So for example, this tree here with these cuts would be an example of a 4 simplex associated to this tree. Okay, now y1 maybe makes a little more sense once I describe the face maps here. So face maps. So just as an example, let me give you a 2 simplex. Labels in. Again, sometimes I've been lazy and not putting the labels. But then I'll take this cut here. And so D0, so we work from top to bottom. So D0 means just throw out everything above the cut. So we would just be left with AB. D2 would be remove everything below the cut. So this would result in the forest. DEF and then C, disjoint from it. And then D1 is just the whole thing where you just forget the cut. And then degeneracy maps insert cuts in uninteresting ways. So again, I'll just start with this same tree. There should be 3 degeneracy maps. So this would be S0, S1, and S2. Let's quickly draw what we start with. So we start with this cut. And then what S0 does is inserts a cut just at the top. S2 would insert a cut at the bottom, and S1 would just duplicate the cut that you had before. All right, so I claim that Y sub t is 2 Siegel. And I'll illustrate this by the same kind of diagram that I've done before. So let me start with a 3 simplex. So maybe I'll have this cut and this cut. And if I had D2, in this case, we would just forget the second cut. D0, as before, would just throw out, well, in this case, the E and the F. Just throw out everything at the top of the graph. And then when you look, so D0 here is going to throw out above the cut. Oh, I'm sorry, and I forgot to put the cut. So we keep the cut that was there, and then this D1 just forgets the cut. And again, the question is, could you recover, if you just had this, could you recover the tree? And this tells you what the whole tree was, and then this part, tells you the extra cut that you would have to put in down. Okay. And it's not 1 Siegel, since you can't, for the same reasons as, sorry, below the screen. You can't always compose. Yeah. Okay. And so you might say, well, if I have a tree, I can either remember that it's a rooted tree, or I can just forget that structure and think of it as a graph. And so we have the following proposition. So given a tree T, Y sub T forms a sub 2 Siegel set of XT, where so the X was the notation for the graph. So we consider the underlying subgraph. Of T. So just as an example, so here was our running example of a graph where we have A, B, and C, but I'm going to draw it suggestively this way. So A is the root. And so now Y1 is going to consist of the empty subgraph, the vertices by themselves. I can always get those from cuts here. And then I have the subgraphs with just singleton edges, or I have the whole thing. Okay, but that's it. So this would be a proper subset of X1. I can't get, for example, where I have this edge from A to B disjoint union with C, because if I separate these from C, that has to be by a cut. And so I can't get C together with it. I also can't, get disjoint unions. Yeah, can't get disjoint unions of various ones of these is the main thing. Okay, but it's worth noting the rooted structure makes a difference. So if I instead put the root at B, so that this would naturally be drawn as a tree in the following way, then I would get a different collection. So I'd still get the empty subgraph, I'd still get the singletons. I could still get these two edges. I guess I should more suggestively draw it this way. But now I could get the disjoint union of A and C. I'm sorry, this is C. By doing a cut here. And then I could get the whole thing. So I could get different things depending on the choice that I make. Okay. And then you can also look at the associated Hall algebras. But since the Hall algebra construction in general is not functorial, something, if you're curious, I think you can go and check from the definitions, but we don't get an algebra map. From the Hall algebra associated to YT to the Hall algebra associated to XT. And we go into a little bit more detail about that. There are some conditions for when the Hall algebras are functorial, but they're kind of strict, and they don't they aren't satisfied here. Another comment is just that HYT is typically not commutative, in contrast. And due to the ordering on the tree. So we don't have pairs of partitions, we just have cuts, and the cuts have an up and a down. So for example, if we just look at the tree with just this one edge from A to B, that if we multiply B with A, then we would get the whole tree. But if we multiplied A with B, we get 0 because there's a directionality there. Okay. So that's just another kind of fun hands-on example. So at the last little bit of time, I want to just sort of talk a little bit about looking towards higher Siegel objects, because I know that's something people have asked about, but I'm not going to be able to say too much, but this will give you a hint at it. Okay, so I think I mentioned in maybe the first lecture that in some sense my definition that I gave of two Siegel spaces was redundant. And I want to come back to that. So this is a result of Dickerhoff and Kapranoff. And it says that, so if I have a simplicial, I'll put this in terms of two Siegel spaces. So a functor delta op, two simplicial sets, is two Siegel, if and only if the two Siegel maps corresponding to the following triangulations. So one of them is going to be, so here's my cyclically labeled n+1 gon. So I can take the triangulation where all the diagonals just sort of radiate out from 0, or I could do the similar thing for everything coming out of the vertex n. Okay. And so it suffices if you just know that the Siegel maps corresponding to these two triangulations are weak equivalences. And this would again, but I'd need to check it. Okay, so as a consequence, let me separate out these two conditions. So a simplicial space is lower two Siegel if the maps, let me label these, let me call these A and B, if the maps for type A triangulations are weak equivalences for every n at least 3, and then upper two Siegel if the maps for the type B triangulations are weak equivalences. Okay, and so a corollary then of that proposition is that X is two Siegel if and only if it is both upper and lower two Siegel. And we very briefly saw lower two Siegel in the second lecture when I talked about if you take at the S dot construction to a category with cofibrations, that will be lower two Siegel, but not necessarily upper. So there are examples of these. And now if we take higher D, we can generalize these definitions. do ones for upper and lower D Siegel spaces. And this uses something called cyclic polytopes. Okay, I think I can quickly kind of say a little bit what these are. So consider the map. So this is the map V from R to R to the D. So this sends a real number T to the D tuple, that's just the powers of T from 1 up to D. And then the cyclic D-dimensional polytope. And you can do this on other sets, but I'm just going to do it on the underlying set of the ordered set N. This is the convex hull of, well, just the vertices. Sorry, not vertices. V event. This is this map V. We'll denote this by C and D. Okay, so a few examples. So if we do C 3, 0, this is just the singleton 0 because the map V just sends, well, there's no tuples here, so this just goes to 0 in the single point of R0. If we have C3, 1, this just looks like, well, we have the points 0, 1, 2, and 3 in the real line, and V is just sending T to T, and we take the convex hull, that's just that line segment from 0 to 3. Then C3, 2, this is where things get a little more interesting. This is not going to be to scale, but so we think of 0, 1, 2, 3. So this is 0, 0, 1, 1, 2, 4, and 3, 9. So T is going to the ordered pair T, T squared, and we get a polygon in this case. And then C3, 3, you can check is, well, fancier coordinates, but it's homeomorphic to the standard topological 3 simplex. And then there is a combinatorial description of upper and lower subsets of N that can be used to define upper and lower D Siegel. And I guess I think this is actually D minus 1 because what you get here when this is, oh no, that's N, not D. Siegel. Recovering the above notions when D equals 2. And fortunately, I don't have time to go into more detail. I can say that these have something to do with n-excisive functors. This is some work of Tashi-Walda. They should somehow arise from higher S dot constructions, so higher dimensional grids. You can see some beginning work on this from Bergner. And then there's some work of, So you could say, well, what's the algebraic structure encoded by D. Siegel? And there's some work by Adam and Elena Gao on this. I think it's still maybe not as straightforward as maybe that it could be, but that's some beginning things. But so there's some things you can go look into if you want to learn more about this. But I am out of time, so I will stop.
All right, let's all thank Julie for the lecture.